Hi everyone, welcome to tutorial 75 of our introductory Python for image processing tutorial series. In this tutorial, let's build on the topic we talked about in the previous tutorial, which is Gabor filters. If you haven't watched it, I highly recommend you to watch it because you'll learn about what a Gabor filter is. And now let's actually see how we can create a bank of filters using Gabor convolutional kernel. So just a quick reminder again, in case you haven't watched the previous tutorial, convolution is where you have a kernel and you're applying that onto an image, and you do this multiplication and update the values wherever you did that, applied that kernel, and then move on one step at a time or two steps at a time or whatever that stride value is. So this is convolution, and Gabor is a convolutional filter where you can change the wavelength, theta, your phase offsets and aspect ratio, whether you want it to be spherical so it's Gaussian, or very narrow so it's almost like a slit type of filter, and so on. So by changing these, you can extract any number of filters. So this tutorial is about how can we change these and create a bank of filters that can be fed into our machine learning algorithm. This is what we call traditional machine learning. And there are people who actually try to do feature engineering, meaning engineer the features to be, to make sure that the machine learning algorithm actually gives the right predictions, or you have the right machine learning, the right way to train your machine learning algorithm. As the computers are getting faster and faster, I think we can actually generate as many Gabor filters as possible. And during the training, especially if you use something like random forest, the algorithm will tell you, hey, these are the features that actually works best on your data. So just remove everything that doesn't work and only keep the ones that actually work. So in a way, let the system engineer the features for us. But for that, we need to generate a whole bunch of features. So let's go ahead and do that. And finally, we applied different types of kernels, and you see the responses right here. So our goal right now is to design a whole bunch of these and save the responses into a pandas data frame. For that, let's jump into our Spider IDE. Let's zoom in a bit so things are clear from your side. Okay, so let's go ahead and load the same synthetic image where we have vertical lines, horizontal lines, and the diagonal lines and everything together. And let's go ahead and read that and convert that image into gray. And I'm using our OpenCV to read these images. Now, this image is 517 by 703, and let's convert that into a single column because, when we add these to our data frames, let's actually add them as columns, each feature. And like I mentioned earlier, the pixel values itself are great features, because if one feature looks pretty bright in the image versus the other, you know how to segment them, right? So do not ignore pixel value. So here what I'm trying to do is reshaping this into a single column and creating a new pandas data frame called df, and adding a column called original image and adding all the pixels right there. So now you can see how I'm actually creating my features and slowly adding them to my original data frame. So if you look at my original data frame, I have these many images with one column, and this column represents the pixel values. And if I keep scrolling down, you should see a bunch of different values, although apparently it is dominated by 255 for some reason. Okay, well, not for some reason, because this image is actually a blank white background with some dark lines on it. So that's the reason why it is fully 255. Anyway, so now we have our data frame defined. Now let's actually get into Gabor. Okay, so first of all, let's start by inside and then start working our way outside. Our kernel is Gabor kernel that takes in parameters like kernel size. Let's move this out so you can see the whole thing. Sigma, theta, lambda, gamma, phi, and whatever that k type is, because this is 32-bit floating, so that's what I provided there. So these are the values I would like to change. In fact, you can even change the kernel size if you want and put that in a loop. So let's just put these in a loop. In fact, the phi also I'm not changing. I'm just leaving it to 0.8 for now. And everything else, let's go ahead and change. So how do you do that? First, I changed the theta in range 4. So we are actually going by steps of 4 right there. And theta equal by 4 times np.pi. So basically here we are going from 0, pi over 4, pi over 2, 3 pi over 4. I think those are the values right there. You can change this to any number, to 8 or something, yeah? So for each of that theta, I'm doing a sigma of 1, 3, and 5. And for each of these sigma, I'm changing my lambda from 0 to pi in steps of pi over 4, very similar to my theta, okay? And for each of that lambda, I'm changing my gamma to 0.05 or 0.5. You can add more, yeah? But these are the values that we are doing. And then Gabor, I just want to save these with different labels. So I just gave a name called Gabor label, and the Gabor label is nothing but just the text Gabor plus whatever that number is. And that's why I initiated this number. So my first one will be Gabor 1, Gabor 2, Gabor 3, Gabor 4. If you want to get even more fancy, you can convert these numbers into strings and add it to your Gabor. So you know exactly what sigma you're using, what gamma you're using for each Gabor. But I'm going to print out that anyhow. So for now, let's just do it this way. And I fixed my kernel size to 15. We can go back to 5 if you want. And my the phase shift, let's go ahead and put it to actually 0. Oh, that was the issue. Earlier in the previous video, I was looking at the kernel and it didn't make sense. And now all of a sudden, okay. And the kernel, we already defined what the kernel is. And then once this is done, I'm going to append the kernel to the kernels, okay? And to this list. And now I'm going to filter it. And the filter is, again, just like in the last tutorial, cv2.filter2d onto my image, okay? In fact, you don't need to apply this to image 2. In fact, we can actually apply this to image itself if you want, and then reshape it. But we can apply this to image 2, and the kernel is kernel, and then we are reshaping it. And finally, I'm writing it down so we can look at all the filter responses as JPEGs. Well, you can change it to PNG if you want, as JPEGs right there. And then this is the key. I'm adding a new column to my data frame with a title Gabor label. You see the Gabor label? In the first iteration, it would be Gabor 1, and then Gabor 2, and Gabor 3. So for Gabor 1, I'm going to add all of these responses that I'm getting from my Gabor filter. Again, if you think this is too much, go ahead and do this step by step, and I hope things will be a bit clear. And finally, I'm going to print the Gabor label. Is it Gabor 1, 2, 3, 4? And for each of that, what is the theta, what is the sigma, what is the lambda, and so on. So this gives me an idea of what's going on. And then now we increase the number by 1, goes back, and then does this iteration. And finally, let's go ahead and print this, or you can save this, all of these into a CSV file if you want. That's pretty much it, actually. So let's go ahead and run this. And you should see that's pretty fast. And let's expand this side so you can see. So there are total 96 Gabors. And as you can see, it started off with Gabor 1, theta 0, sigma 1, lambda 0, gamma 0.05, right? All of these are constant. And the inner loop for gamma, it goes from 0.05, 0.5. Once it's done, it goes back to gamma 0.05, but then it changes the next one, right? I mean the lambda, and then does it for different lambda. And then it goes on and changes the sigma, and eventually it changes the theta. How many times? Well, apparently 96 filters right there. So if you look at our data frame, we should have 97 columns. It says tremendous amount of data. Do you want to open it? Let's open it anyway. And as you can see, the first column in our data frame right here is the pixel value from original image, and then Gabor 1, 2, 3, 4, 5, 6, all the way up to Gabor 90 something. And this is the table or data frame that goes into my machine learning algorithm, whether it is support vector machines or random forest, to do the training and generate a model. Okay, so I hope you found this tutorial to be intuitive. You will have to go through this a few times. All we are trying to do is use the Gabor kernel and change the theta, sigma values, lambda values, and all of these, and create a whole bunch of these. Now, one thing we didn't see here is I'm applying that filter onto my image and actually saving those. So if I open this, in fact, let's view large icons so you can actually see the Gabor response. In fact, let's look at extra large icons so you can see the Gabor filter responses. The input image is something like this, where you have horizontal, cross, vertical, and all of this. And this is useless, that's useless because I'm not getting any response here. And these two are also probably not that useful if I want to separate these into 4 or 5, 6 different classes, but a combination of all of these may be valuable. Okay, here you see the missing one. The vertical is missing. Now, if you think this is not giving the right response, maybe these 90 are not enough, and you will have to go back and for theta in the range 8, for example, and change this to 1, 3, 5, 7, and 9 for sigma, and change all of these, and then actually get different parameters. So let's go ahead and run this one more time, and now you can see the images being hopefully updated as they are running. So let's go ahead and now we should see a lot more. Now 170, 180, 190. These are very fast. Well, even on images that are 500 by 700. But now because we have done it, let's go ahead and see it. So there you go. A lot more responses right there. So this is how you can generate a whole bunch of filters using Gabor. And in the next tutorial, let's understand a actual machine learning algorithm so we can apply this plus the machine learning to start segmenting our real world images. I hope you found this tutorial to be useful, and let's meet again in the next tutorial.